In this video, we'll be talking about how putting everything we've learned together to factor a polynomial. So we saw in video 2.5.1 that the linear factorization says that we can actually factor any polynomial into linear factors, i.e., after pulling off the leading coefficient, a, factoring it all out, we should be able to factor this into x minus c1 times x minus c2 all the way down to some x minus cn, where c1, c2, all the way up to cn are complex numbers in general. And there may be some repetition, right? I mean, you might have a repeated 0 or something. But in general, if you count all the repetitions and you allow complex numbers, you should get exactly n of these linear factors for if our polynomial is of degree n. In light of the last video, we also know that conjugate pairs come together when f has real coefficients. Thus, since multiplying conjugate factors creates a real coefficient quadratic, we can also say that every polynomial of degree n greater than 0 with real coefficients can be written as a product of linear and quadratic factors of real coefficients. Namely, we can get rid of all these c's, but we might end up with some quadratic factors because all of those conjugate pairs come together to create these quadratic factors with real coefficients. So, for example, if we wanted to sort of see how this works in general, let's find all the zeros of this function, assuming that we know 1 plus 3i is a 0 of f. Well, first off, if 1 plus 3i is a 0 of it, then we know that 1 minus 3i must be a 0 as well. It is also a 0. So, we can get a real quadratic. And this is what we were saying in the last, a real coefficient quadratic. By the way, well, I'll say this after. Anyways, that is, we know that x minus 1 minus 3i and x minus 1 plus 3i are both factors, but we're going to put these together to get a quadratic. Once we do that, so let's go ahead and do that, we would have x squared minus x minus 3ix. Then we have minus x plus 1, negative 3i times negative 1 is plus 3i. And then putting positive 3i through would be plus 3ix minus 3i. Then negative 3i and positive 3i would be negative 9i squared. Well, the 3i and that will cancel, that and that will cancel. All the i's should go away if you're doing this right. And the I squared will become a negative 1 here, as always. And so we have x squared minus 2x. We have a plus 1 here, but then we also have the plus 1 and the plus 9 will come together to give me a plus 10. And so we get this. This is called a, this is also called, because we cannot, this only has complex zeros. This is called an irreducible. This is called irreducible over the reals, which means we can't really break it down any further using just real numbers. We need complex numbers, okay? Just a little bit of terminology. Anyways, continuing in the continuing in this, we now know that this whole thing is a quadratic factor of this. Well, if that's the case, we can now divide out by this to get to break this down further. So we have x to the 4th. Well, so let's do the division then. Oh, we have to do long division because this is a quadratic. So can't use synthetic, darn it. x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. To match the term, we need an x squared. X to the fourth, 2x squared, 2x cubed, sorry, 2x cubed, 10x squared, and then we reverse all the signs, negative, positive, negative. Those would cancel. We get negative x cubed minus 4x squared, bring the 2x down. We end up with what? We would have, we need to match this term, so negative x cubed, 2x squared times a negative, so positive, but then it's going to flip everything. So I'll worry about the sign, so let's just write it down, plus 2x squared minus 10x. But then we change all of our signs. Ugh. Cancel, negative 6x squared, 12x. And now we go through and bring the negative 60 down. I've run out of room, but to match that, we're going to mean minus 6. Putting that through, we'll end up with positive 6x squared, positive 12x, negative 12x. Once we change all the signs, and positive 60, and thus everything cancels, which makes sense. And so what we get is we now know that we can break this whole thing down into x squared minus 2x plus 10, which is irreducible, and x squared minus x minus 6. So now we just need to factor this. Well, this factors easily into x minus 6 and x plus, x minus 3 and x plus 2. So here we have x squared minus 2x plus 10, which means all of our zeros are in fact 1 minus 3i, 1 plus 3i, and 3 and negative 2. So there you go. So now let's have you try an example. Let's go ahead and find all zeros of x cubed minus 2x squared plus 48x minus 32, given that you already know 4i is a 0 of f. On the count of 3, I'll reveal the solution. 1, 2, 3. So I actually made a typo first, so keep that in mind. There should be a 3 there. I messed up. Once you have the 3 there, this works though. You know that negative 4i must also be a 0, so x plus 4i and x minus 4i are both factors. Put them together, you get x squared plus 16. This is our irreducible quadratic. Divide it out, and you get out of here, you get x squared plus, you get 3x minus 2 as the other factor. So this must be able to factor into this, which means that x equal 2/3 must be our other 0. And so putting them all together, we have that. Let's do another example of how to sort of factor something in general. So let's go ahead and write f of x equal x to the 5th plus x cubed plus 2x squared minus 12x plus 8 as a product of linear factors, and list all zeros of the function. Oh boy, this is a big problem. First things first, we need to try to guess rational zeros. So first, find a rational zero. 0. What are the possible rational zeros? Well, here we see that p over q can only be plus or minus 1. P could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So we have plus or minus 1, plus or minus 2, plus or minus 3, 4, and plus or minus 8. So we have 8 different possible rational zeros here. Let's try to guess some. If we do f of 1, let's just start with the first one and start plugging in. Plug 1 in, you get 1 plus 1, which is 2, plus 2 is 4, minus 12 is negative 8, plus 8. Hey, look, that's a 0. So we can divide out by the 0, 1. Dividing out by the 0, 1, we have 1, 0 is our x to the fourth term, 1 for x cubed, 2, negative 12, and positive 8. And this should give us a remainder of 0. 1 and 1 gives me 1, 2, 4, negative 12, plus 4 is negative 8, 0. Good. And this leaves us with a slightly smaller polynomial. Well, here, so we end up with x to the fourth plus x cubed plus 2x squared plus 4x minus 8. And now, again, we try to guess another rational 0, right? What about, let's try 1 again. 1 and 1, because 1 could be repeated. 2 and 2 is 4. 4 and 4 is 8. Hey, look, x equal 1 is another 0, right? F of 1 equals 0. So 1 is repeated in this case. Here we have 1, 1, 1, 2, 4, and negative 8. 1, 2, 2 and 2 is 4, 4 and 4 is 8, 8 and 8, negative 8 and 8, 0. Good. So now we're down to x cubed plus 2x squared plus 4x plus 8. This we can now factor by, we can factor the rest of this by grouping, interestingly. So let's factor by grouping. We get x cubed plus 2x squared plus 4x plus 8. And in general, you should always, once you get down to a cubic, you should ask, can I factor by grouping? If you can't, then you kind of need to continue this process, right? Here we can pull out x squared, x plus 2, plus 4 times x plus 2. Because these are the same factor, this is how you know if grouping works. Because these are the same factor, we can pull it out. We have x squared plus 4 times x plus 2. Well then, what do we have? So yeah, so far what we have is we have x plus 1 that we pulled out before up here. Then we pulled out 2 x plus 1s here, right? So far what we have is we now have x plus 1 squared times all of that. Well, we're almost done now. Now we just need this part, right? Here, this will factor, this is an irreducible quadratic over the reals, but we know that plus or minus 2i should be the zeros of it, saying it equal to 0. So we get the zeros. Let's go ahead and box in our solution. The zeros are going to be negative 1, because of the 1 and 1. Sorry, this is x minus 1, right? Yeah. There we go. 1, 1, negative 2, and 2i and negative 2i, which means we can write f of x as x minus 1 times x minus 1 times x plus 2 times x plus 2i, x minus 2i. All right, and that's our linear factorization. Now it's time for you to try an example. A brief hint on this before you get started. Try thinking of this as a quadratic with x squared as your variable. But anyways, go ahead and try working that out, and on the count of 3, I'll reveal the solution. 1, 2, 3. So here, pretending that x squared is sort of our variable, we see that this becomes a simple factoring problem. Namely, we'd have x squared plus 9 and x squared minus 1 here. Then solving each of these out for their zeros. The zeros of this would be plus or minus 3i. The zeros of this would be plus or minus 1, which means our total list of zeros are 1, negative 1, 3i, and negative 3i. Thus, the factorization corresponding to that would be x minus 1, x plus 1, x minus 3i, x plus 3i. You could go ahead and break both of these down into those as well, but it's easier to just look at the zeros. If you'd like some more practice with these sorts of problems, be sure to see page 162 and 163 of the textbook and work problems 5, 6, 51 through 72. In our next video, we'll go through a couple more tests that can kind of help you when trying to find zeros of polynomials.